So today is the 10th of November. So I just want to continue with Lewis structures. So from here on out, we'll just do some practice Lewis structures. And, once I make the exam, I'm planning it to be the last day of class. I'll give you more information on that. So 24th. And right now, I'm planning it to be 25 multiple choice questions on Canvas. And maybe, if I have time, I'll have a take-home portion like before. But right now, I'm just looking at just 25 multiple choice questions on Canvas. Maybe a take-home. Depends how much I can get done. And which also means a couple of other things I want to tell you guys. A couple of other things I want to tell you guys is I'm going to have class Thursday, okay? So you can come if you want, if you'd like for you to come. If you can't come, then you can watch the recording, all right? So come to class on Thursday. This was originally a Tuesday, Thursday class, but realizing very few people are coming, so we'll just have it Tuesday, Thursday. So you can come Thursday. So there will be class Thursday. If for whatever reason you can't make it to class, it will be recorded. Okay, so class on Thursday with new lecture, new material. Again, if you cannot make it, please watch the recording that will be posted a little bit afterwards. And so the labs are done, so make sure you turn in your lab reports. And make sure you turn in your lab notebook. Okay. I don't have a firm due date other than I can tell you the class ends November 24th, so I can give you a firm due date, but I'll accept them if need be. Okay, your lab notebook. All right, so turn that in for those of you that were doing the labs with us. Anything else you can think of?
Does test 4 have the
quiz 4 is due. Thank you. Indirectly reminding me. Yes, go ahead.
Does it have the problem set?
I haven't made it yet, so I have not even made this. This is what I'm planning. Okay, so that's it. Yeah, it's going to be the same format as test 2. It says test 1, test 2, test 3, and test 4. I just haven't made this test yet because I've been very busy with other stuff going on. And once I make it and make the study guide, I'll put it up on Canvas. Also, quiz 4. Some of you may use this as a drop. Some of you will still turn it in. Whatever it is, that's there, and I'll grade it like I've been grading all of the quizzes. And I think that's it. There's this tutor thing, clutch prep. So I don't know how much you guys are doing that. Okay, this is only to help you, especially if you're taking chemistry 2, sort of reinforce certain principles and concepts. So make sure you do those drills. And this will only for helping purposes, not for giving you extra stuff to do. Okay? Anything else?
The extra credit?
Yes. Since we have a couple of... Yeah, I was going to comment on that, but it's a good time to talk about it. So I have 40 Lewis structures, okay, that you can do. Basically, you draw the Lewis structures and check your answers with my answers. It's totally the honor system, and it's extra credit. It's just practice. And if you do that, I'll give you 25 points extra credit.
I was having some trouble needing to check my answers with the solution sets. I don't know if that was just something on my part, but I was clicking on to check, and then it said like unauthorized, and then the link next to it said like wasn't
Okay, so let me look into that. Okay, thank you. Okay, that could be on my end. I'm still learning Canvas, so yeah. I mean, it's possible. So I'll look into that, where the solutions are. But that's just practice. And this due date, I haven't made a due date, excuse me. But yeah, it's a good idea to start working on those for practice. Anything else you guys can think of? Yeah.
This might be a simple question. Is test 4 our final, or is there a formal final?
No, that's it. Yeah, there's no final. Okay. And it's not cumulative. This will cover chapter 7 through 10. Okay, 7, 8, and actually, to be honest, Tiana, 9 and 10 I joined together. So it's really 3 chapters. Yeah, anything else? So on my end, I'll give you more firm due dates. Meanwhile, upload whatever you can upload on your Canvas so that I can put the points in. Okay. Quiz 4, test, I still haven't made it. For those of you that want to attend class Thursday, I'll have a class. If you cannot make it, perfectly fine. Just watch the recording. Whatever lab reports you need to turn it in. Turn in your lab notebook sometime soon. Okay, I'll put in the 100 points. Quiz 4, do those clutch prep to help you with the lecture. And I will look into that, Bethany, about the answer key for the Lewis structure problems. So I thought I would just go and talk a little bit about Lewis structure, some practice. I think last time we met, I told you some rules. Okay, so now we're going to put those rules into motion. Okay, and let's go ahead and do that. How about the most simplest one here? Okay, the most simplest one is CH4. Okay, this is easy. This is called methane. All right, carbon loves 4. All right, so carbon is happy at 4. Hydrogen is happy at what number? Okay, 1. But how many hydrogens do we have? We have 4. Okay, so 4 plus 4 is 8. Okay, so our goal is to get 8 valence electrons around the methane CH4 molecule. Okay, carbon must have 4. 4, 4, 4. So our center atom is carbon. 4, right? 1, 2, 3, 4. Okay, this is as easy as they come. Okay, methane. Okay, a couple of things we need to do. Let me get some extra pants here that I got from home. A couple of things we need to do as we get more and more complicated. We need to minimize formal charge. Okay, you see here CH4 has no charge, so there should be no charge here. Okay, formal charge. Let's see if we remember this from last week. Okay, formal charge. Count with me. 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4? 0. So the formal charge on that carbon is 0. All right. Also, we can do the octet rule. Okay. For the octet rule, we need to count everything individually. Okay. For the octet rule, we count everything individually. So for this carbon, okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the octet rule for that carbon is satisfied. Let's do the same thing for this hydrogen. Formal charge of this hydrogen. Okay, ready? Okay, 1. What is hydrogen happy at? 1. What's 1 minus 1? 0. Okay, let's do the octet rule for this hydrogen. Okay, 1, 2. Is that satisfied? Yeah. Okay, the octet for hydrogen is 2. Remember, the octet rule has a lot of weirdness to it. Okay, you can have an expanded octet. You can have a incomplete octet like hydrogen, aluminum. Okay, they're all incomplete octets. All right, this is not how it looks like in 3 dimensions. All right, so let's look at our center atom. So this, I think, is new information. our center atom is going to be carbon. Okay. How many bonds attached to this carbon? Okay. Single bond is 1. Another single bond is 2. This third is a single bond. And then finally we have 4 single bonds. So we have 4 bonds, 0 lone pairs. Okay, 4 bonds and 0 lone pairs. So I hope I have this table. If not, 4 bonds and 0 lone pairs. We're going to go to table 10.1. Let's see here. I don't have it. So 4 bonds and 0 lone pairs. You're going to use table 10.1 in your textbook. I guess I can go to my office and get it, but that's fine. So on your exam, you want to use table 10.1 and 10.2. So on your exam, you'll use table 10.1 and 10.2. And what tables 10.1 and 10.2 tell you is the geometry of the molecule. Okay, the geometry. Haha, I got it. No, I didn't. No, sorry. I got it. All right, so 4 bonds, 0 lone pairs. Why 10.1? Again, you can bring this to the exam, or I can put a copy up on the Canvas exam. So why am I asking for 10.1? Because 10.1 is the table in which the central atom, okay, look what I'm highlighting here, has 0 lone pairs. Okay, no lone pairs. And here we have no lone pairs. Okay, so 4 bonds and 0 lone pairs, right? Everyone double check. 4 bonds, 0 lone pairs. The geometry, okay, is tetrahedral. Okay, so that is the shape of this molecule. So let's see if we can show what CH4 looks like, quote unquote, in 3 dimensions. Normally I'd bring people up, but because of the distancing, I'll just go ahead and construct this. Otherwise I'd have you come up or just come up. So 4 bonds, 0 lone pairs. I got my PhD in a structure biology lab, so my PhD mentor loves the structure. She loves all this stuff. So definitely a very wonderful, smart, brilliant woman. Anyways, this is CH4, okay? Tetrahedral. So this is what it looks like. Right? No lone pairs. We have beautiful bond angles, perfect bond angles of 109.5 degrees. So let's see if we can draw this in 3 dimensions. Okay, so that's our next goal. See if we can draw this in 3 dimensions. So here's how we'll do that. Okay, so I'm going to draw my carbon here. Okay, I'm going to draw my H here. Okay, I'm going to have another H here. Okay, I'm going to draw a special bond. It's called a wedge. Okay, so this is trying to draw something 3D on a 2D piece of paper. Okay, so the name of this bond is called a wedge. And then I'll have something come back. Okay, this is called a dash. And there's more than one way to skin this cat. There's more than one way to draw something that's three-dimensional. But this bond is called dash. You see the dash bond is going away from the board. It's going away from you. And the wedge in this that's colored blue is coming towards you, okay? And that's how we would depict, this is how we would depict a molecular geometry that's tetrahedral. So the molecular geometry is tetrahedral. So let me show you something. I don't know. Some people have this naturally, some people don't. I used to mentor an undergraduate when I worked in a lab, and he went to dental school. He's a dentist now, actually. So he was able to see things in 3 dimensions. He'll look at this and like the mouth, the jaw. He just sees things in 3-dimensional arrays. So he's a practicing dentist now. But I'm drawing this tetrahedral like this, okay, on a 1-dimensional sheet of paper. But let me see if you can see this. Not all can see this. But if I'm going to draw the center of every atom, okay, with a dot, okay. So that little blue dot is the center, and I'm going to connect the dots. And I don't know if you guys can see this or not, but if you connect the dots, you should see something that is, again, your professor's not Picasso, but you should see something that is tetrahedral, okay? Something like this. Some people can see it with their eyes, others can't. I know for me it's a little difficult. So this is what it looks like in 3-dimensional space. The easiest Lewis structure there is. Very nice clean bond angles, 109.5 degrees. And finally, I want to tell you guys something called hybridization. Hybridization basically means mixing of orbitals. Okay. So we have 4 bonds, 0 lone pairs. 4 plus 0 is 4. So in order to get 4, okay, I'm going to take 1 from S. P actually has 3 slots. So this is 1. This would be 2, 3, 4. That's how I will get my 4. So this is an sp3 hybridized carbon. Okay. 4 plus 0 is 4. So 1 from S, and then the 3 from P, because P has 3 slots. So this is an sp3 hybridized carbon. Hybridized carbon. Okay, so we have to know our molecular geometry. We have to know the hybridization. Okay, 4 bonds and 0 lone pairs. Okay, no lone pairs. We're going to use this table. If there's lone pairs, we'll use this table here with lone pairs. And then finally, this is a nonpolar molecule. Okay, there's nothing electronegative. There's no pull. Okay, there's no oxygens, there's no fluorines, there's no electronegative elements. So this is a nonpolar molecule. Okay, there's no partial positive, there's no partial negative, nothing. Okay, so it's a nonpolar molecule. So that is CH 4, and that's the easiest one in terms of the Lewis structures. Okay, let's keep on doing some more for this class until. So let's look at water. Okay, this is something that's also kind of simple. All right, so oxygen is happy at 6. Okay, what is hydrogen happy at? 1. Okay, but we've got 2 hydrogens. Okay, oxygen happy at 6, hydrogen happy at 1, but we've got 2 hydrogens. So 6 plus 2 is 8. So our job is to get 8 valence electrons around the water molecule. So I'm going to make oxygen my center atom. Okay, why oxygen? Because I don't know which hydrogen. Is it hydrogen 1? Or is it hydrogen 2 that's going to be my center atom? So let's just make oxygen our center atom. So I'm putting a hydrogen here. Okay, and another hydrogen here. All right, so 1, 2, 3, 4. Okay. 1, 2, 3, 4. Where do you think 5, 6, 7, and 8 will go? Okay, it's not going to go on the hydrogens. But 5, 6, 7, and 8 will go on the oxygens, the center atom. Okay. So that's how I will get my 8 valence electrons around H2O water. All right. And let's look here, formal charge on this oxygen. Okay, ready? Formal charge. You can count with me. 1, 2, 3, 4, 5, 6. What is oxygen happy at? 6. What's 6 minus 6? 0. So that oxygen will have a formal charge of 0. And let's do the octet rule for this oxygen. Okay, we count everything one by one individually for the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. So this octet rule is satisfied for that oxygen. Hydrogen, okay, this hydrogen and this hydrogen are the same. So count with me. Formal charge on this hydrogen, 1. What is hydrogen happy at? 1. 1 minus 1 is 0. The octet rule for this hydrogen, 1, 2. Okay, hydrogen has, that's the octet rule for hydrogen is 2. Okay. All right, so looking at the center atom oxygen, we have 1 bond, 2 bonds. We have 1 lone pair here and 1 lone pair here. 2 bonds, 2 lone pairs. 2 bonds, 2 lone pairs. Everyone see that? 2 bonds, 2 lone pairs on the oxygen center. Okay, we're only concerning with our center atom. 2 bonds, 2 lone pairs. So this would be a good candidate to use table 1, table 10-2, lone pairs. All right, so here we go. Everyone look here, 2 bonds, 2 lone pairs. Look, they even give you the example. What's the geometry? Bent. Okay, a lot of people think water is a linear molecule. I don't know if it was this section, but I taught at Fort Bragg. I asked, this was a biochem class, what is water? It's a very important topic in that course. Someone said water is linear, but nothing can be further from the truth. Okay, water is not linear. Okay? Water has this geometry which is bent, and that's super important, super critical for the biology, it's super critical for biochemistry, and that bent structure of the water molecule. So it's almost like the 2 lone pairs are doing this. Okay, they're bending the water molecule. So the molecular geometry is bent. Okay. The bond angle for water is actually unique. Okay, I do not know the actual bond angle. You can look it up, I'm sure, on Google. But of all the molecules, there's millions of molecules on the face of this earth. No other molecule has the bond angle of water, the HOH bond, which I think is 108 something. Okay, it's a weird bond angle. Again, another reason why people think water has some of these remarkable properties. All right, hybridization now is something I want to talk to you guys about. 2 plus 2 is 4. 2 plus 2 is 4. How will we get to 4? Okay, well, we can take 1 from S. And how many can we take from P? Okay, we have 1 from S. 2 plus 2 is 4. How many can we take from P? We'll take 3 from P. Okay, so this is an sp3 hybridized oxygen. 1s is 1, and then 3 of the p's. So 3 plus 1 is 4, and that will give me the 4 bonding that I need. 4 bonding, 2 of which are bonds, 2 of which are lone pairs. Probably the lone pairs are going to go to one of the p orbitals. Okay, but it's an sp3 hybridized oxygen. Okay, so we got our hybridization down. We got our geometry. This is what it would look like in 3-dimensional space. Okay, so basically we will move 2 of these. It's the water. Look what the lone pairs of electrons do. Okay, again, it's not linear. It's kind of like this. Again, probably one of the reasons why water is so important in our cells and in nature and all of that stuff. The sort of bent properties, the bent geometry. The molecular geometry is bent. Finally, this is definitely very important again for biochemistry and biology. This is definitely a polar molecule. Okay, you see the oxygen is pulling this way. So within that oxygen, you have a partial negative, leaving this partial positive. You see, this is not a 50-50 bond. Okay, it's not shared equally. Same thing on the other side. Oxygen, your fluorines, your halogens, your nitrogens, all of those, they pull. They have electronegativity. They're like a vacuum cleaner. Okay, a lot of sucking power. So same way on this side, it's pulling. So you draw a little line, put your arrow in, make sure you leave a tail, and partial positive end. So this is polar. Okay, it's definitely polar. Water. Okay. Truly an amazing substance, the water molecule. All right, let's do some more here. Okay, how about CO2, carbon dioxide? Okay, this is important, especially for biology majors or environmental science majors, carbon dioxide. All right, so carbon is happy at 4. Okay, what is oxygen happy at? 6, but we have 2 of those, so 12. So our goal is to get 16 valence electrons around the CO2 molecule. Okay. So let's make our center atom carbon, because I don't know which oxygen will be center. So I think it's easy for us to make carbon the center. So we'll have carbon as the center, and then carbon must have 4. Okay, if there's anything you learn from my chemistry class, learn that carbon loves 4. Okay, so how will we get to 4? Single bonds. Okay, how will we get to 4? Here's 1. Okay, we'll do another bond to the oxygen here. How will we get to 4? Okay. So 1, 2, 3, 4. So 2 double bonds will do that. All right, so 16 valence electrons. All right, 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, that would be the structure of carbon dioxide. All right, let's do our formal charge and octet rule stuff. Formal charge of this carbon. Okay, ready? Count with me. 1, 2, 2, right? 3, 3, 4. What is carbon happy at? 4. What's 4 minus 4? 0. All right, let's do the octet rule for this carbon. Ready? Now we got to count everything individually, shared and unshared individually. Individually means this, so count with me. 1, 2, 3, 4, 5, 6, 7, 8. Okay, the octet rule is satisfied for this carbon. All right, let's look at this oxygen, realizing I'm going to do one oxygen is the same for the other. One oxygen is the same for the other. All right, so the formal charge for this oxygen. Okay, ready? Count with me. Formal charge now. Okay, everyone, formal charge. 1, 2, 3, 4, 5, 6. What is oxygen happy at? 6. What's 6 minus 6? 0. Okay, so the charge on that oxygen, it's called formal charge. The charge on that oxygen is 0. Okay, octet rule. Here you count everything individually. So ready? 1, 2, 3, 4, 5, 6, 7, 8. The octet rule is satisfied. This is the best structure of CO2. This is the best. Any other way would have something weird with the charges and such. All right. So let me focus your attention on this center carbon. All right. We have how many bonds? One bond, which is a double bond. And then we have another bond, which is a double bond. Total of 2. Okay, how many lone pairs? Do you guys agree? 2 bonds, 0 lone pairs? Right? 2 bonds, 0 lone pairs. So here we'll use 10-1. Okay, why am I using 10-1? Because of 0 lone pairs. So 2 bonds, 0 lone pairs. 2 bonds, 0 lone pairs. It's linear. Okay, straight line. Straight line. Molecular geometry is linear. All right, 2 bonds, 0 lone pairs. What's 2 plus 0? 2. So what will I do in terms of my hybridization? Okay, how will I get to 2? I'll take 1 from S, and then how many from P to get 2? 1. Very good. So this is an SP hybridized carbon. Okay. Only concerned with the center atom. SP hybridized carbon. Right, and finally, you see this oxygen. Okay, it's pulling this way. Okay, so it's going to pull this way. Okay, electronegative. Okay. What about this oxygen here? Okay, it's doing the same thing, right? It's pulling in its own way. Partial negative here going that way, partial negative there going the other way. Okay, I want to tell you they cancel each other out. Okay, they cancel each other out. Okay, this vector, I don't know if you've studied vectors. Okay, this vector totally negates, totally offsets that vector. The poles are opposite, equal and opposite. Because they cancel each other out, this is a non-polar molecule. Okay. Non-polar molecule. because the arrows are equal and opposite directions. All right, so carbon dioxide linear, nonpolar, sp hybridized carbon. sp hybridized carbon. Looks like a straight line. Shall I bore you with this? Okay. 180 degrees. Top angle, 180 degrees. All right, let's do what's next on our list here. Okay. How about this one? Let's get a little tough now, okay? Okay, how about this one? Okay, XeF4, okay? XeF4, this is called xenon tetrafluoride. All right, what is xenon happy at? Okay, xenon is going to be happy at 8. It's a noble gas. It will be happy at 8. Okay, so xenon is happy at 8. What is fluorine happy at? Group 7. What's group 7 happy at? Fluorine and the halogens are happy at 7. Right? Fluorine is happy at 7. How many fluorines do we have, Elena? 4, right? 4. Okay, so our goal is to get 36 valence electrons around xenon tetrafluoride. Okay. So let's make xenon our center atom because, see, I don't know which one of my 4 fluorines is going to be center. Okay, let's just make xenon center. Okay, and then fluorine. Fluorine. Okay, this is one-dimensional, so you know. Okay, so there's my XeF4. All right, so 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now count with me. 9, 10, 11, 12, 13, 14. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Where will 33 and 34 and 35 and 36 go? Okay, they will go on the xenon. 33, 34, 35, 36. Okay, so now I've got my full 36 valence electrons accounted for. Okay, so the 2 lone pairs go back to the xenon. All right, let's, why did I draw it like that? Well, first of all, the other lone pairs cannot go on the fluorine. They don't go on the outer atom. Okay, fluorine, chlorine, halogens, happy at 7. Okay, happy at 7 no matter what. So let me do the formal charge of the fluorines here. So count with me. Okay, ready? 1, 2, 3, 4, 5, 6, 7. Once again, 1, 2, 3, 4, 5, 6, 7. What is fluorine happy at? 7. What's 7 minus 7? 0. Let's do the octet rule for this fluorine. All right, octet rule, we count everything. Everything one by one. So count with me. Okay, so octet rule. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, even though it's shared, it belongs to fluorine also. So 1, 2, 3, 4, 5, 6, 7, 8. This has an octet. Okay. So perfect. Fluorine, 0. Octet, everything is good. All right. It's the same for this, and that fluorine. I don't want to bore you with doing all of that again. All right. What about the formal charge of this xenon? Okay, ready? Formal charge, count with me. 1, 2, 3, 4, 5, 6, 7, 8. What is xenon happy at? 8. What's 8 minus 8? 0. Okay. Let's do the octet rule for xenon. Okay. Ready? You count everything individually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's okay. That's okay. We call this an expanded octet. There's a lot of wishy-washiness with the octet rule, but that's okay. Why is it okay? Because I got my formal charge to be 0. Okay? You see, if I give you this problem on the exam, there's 0 charge, so there's 0 charge here. Okay? All right, looking at the center xenon, we have 1 bond, 2 bond, okay, single bond 1, single bond 2, single bond 3, single bond 4, and then lone pair 1, lone pair 2. So 4 bonds, 2 lone pairs. This is where we're going to use table 10.2. 4 bonds, 2 lone pairs. All right, everyone see that? 4 bonds, 2 lone pairs. And what is that? Okay, why am I using 10.2? Because of lone pairs. So where's that here? Bonding pairs, 4. Number of lone pairs, got to go all the way down here. 2. And the geometry, messing this up. The geometry is square planar. Okay. Look, they even gave you the example XCF4. So XC. So XCF4, that's having a hard time making up its mind, right? So XCF4 is the molecular, XCF4 is the molecule. The example, the geometry is square planar. 4 bonds, 2 lone pairs. So square planar is the molecular geometry. So you bring this and table 10.1 for the exam, and I'll put a copy up on Canvas for you to access. So the molecular geometry is square planar. Four bonds, 2 lone pairs. 4 plus 2 is 6. How will I get to 6 when I do my hybridization? Okay, I'm going to take 1 from S. Well, I can take only 3 from P, right? Because P has only 3 slots. So where else will I take next? I'll take from D. Okay, I'll take from D. So 3 plus 1 is 4. How much do I need to take from D? 2. Yeah. This is an sp3d2 hybridized xenon. Okay, 1 from S, 3 from P, and then 2 from D. Okay, probably those 2 lone pairs sit on the D orbital. I don't know. Okay, it's just sp3d2 hybridized xenon. And then finally, is this polar or non-polar? Well, look at this carefully with me. You see this fluorine is going to pull this way. And what will this fluorine do? Okay, I hope I can convince you that it does the opposite. Okay. What about this fluorine? I'll do that in this green color. Pulls this way. Okay, what will this fluorine do? The opposite. Okay, what about this pair of electrons? Okay, this pair of electrons on the top is pulling in its own way. What about the bottom pair of electrons? Pulling in the opposite way, yeah. Partial negative cancels out with this partial negative. This partial negative cancels with that one. The up cancels with down. This is a non-polar molecule. Okay, it's kind of tricky, but they all cancel. Okay. A non-polar molecule. So let's see here. 6. This is what xenon tetrafluoride would look like. Looks like a big X. Okay, flat looks flat here. Looks like an X. But what I could do is, there's many ways to draw this three-dimensionally. I could flip it 90 degrees, and now it's pointing towards you. Fluorine, fluorine, and this fluorine towards me, this fluorine towards me at an angle. Okay. So there's many ways to draw this 3D. Let me draw this for you. Okay. Square planar. Alright, so these two fluorines pointing towards you guys at an angle, Tiana and Elena. So like this. Okay, and this fluorine going back. Okay, here's an electron here. Whoop. There's an electron down there. So we'll just, I guess what I'm trying to tell you guys is that there's many ways to draw this in 3D. So that's one way. Okay. Another way I can draw this is like this. Okay, now these guys are flat. Okay. So just doing a 90-degree flip on the plane, on the plane, on the plane of my chest, on the plane, and then this lone pair of electrons going towards you guys. So maybe again, many ways to draw this. And then this one here is going back. Yeah, okay. So trying to draw something 3D in 1D piece of paper. So shown here is like this. Fluorine's coming towards you guys. If I do just a flip, I'm getting this. Okay, here the electrons are going towards you and behind you. Oh, I'm sorry. There. Thank you. I think I'll end that. Time to move on. I will do more of these on Thursday. Now what I'd like to do is talk to you about resonance. That's the next main topic for you guys. Resonance. Right, so we'll put a halt on our practice and then resume it on Thursday. Okay, resonance. Okay. Basically, these are hybrid structures. Okay, so there's more than one structure that can exist, but they are equal. Okay, more than one equivalent. Okay, I'm going to put the word equivalent in caps. So as an example, let's do, remember our flashcards way back when? Okay, one of our flashcards we had was called the nitrate ion. Okay, the nitrate ion. So let's do this as an example of resonance. So N is happy at 5. Remember, N is happy at 5. What is oxygen happy at? 6. Okay, but we've got 3 of those, so that's 18. Okay, the electron, we add 1 electron. Okay, why are we adding an electron? Okay, because of the minus sign. Okay, so our goal is to get 24 valence electrons around the nitrate ion. Now let's just step out from this problem a little bit. Let's just step out. I want to tell you something. Okay? I'm hoping if you use this little tool, it will make the Lewis structures easy. All right. Okay, let's step out here, taking you out on a tangent. And then I'll bring you back. All right, so forget about this R for a moment. But if I have an R with a single bond to an oxygen, okay, an R with a single bond to an oxygen, I'll have 3 lone pairs here. Okay, so this R is an atom or whatever, okay, but it's a single bond to an oxygen. All right, let's count the formal charge in the octet rule for this oxygen, realizing it's a single bond to that oxygen. Okay, ready? Formal charge. Count with me. 1, 2, 3, 4, 5, 6, 7. What is oxygen happy at? 6. What's 6 minus 7? -1. So that single bond oxygen will have a minus formal charge. Okay, let's look at the octet rule. Okay, count with me. Octet. 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. Okay, the octet rule is satisfied. All right. One more thing I want to tell you guys before I take you back to this problem. Okay, forget about this R for a moment. Okay, it's just a whatever atom or something. Okay, focus on that R or whatever forming a double bond with the oxygen. Okay, this time, basically what I'm doing here is, this. Okay, forming a double bond with the oxygen, and now we have 2 lone pairs. Okay. All right, let's do the formal charge and octet rule with me on this one. So count with me. We'll first do the formal charge, everyone as a class. So formal charge on the double bonded oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What is oxygen happy at? 6. What's 6 minus 6? 0. Okay, let's do the octet rule on this double bonded oxygen. Okay, ready? Octet, we count everything. 1, 2, 3, 4, 5, 6, 7, 8. The octet rule is satisfied. So the formal charge on that double bonded oxygen is 0. Okay, forget about whatever, all that stuff. The formal charge on the single bonded oxygen is negative 1. Okay. All right, let me take you back to this problem here. Now let's do the structure of nitrate. Let's make nitrogen our center atom, because you see I don't know which oxygen will be center. Is it oxygen 1, 2, or 3? We don't know. So we'll make nitrogen the center atom. Okay. We have 3 oxygens. 1, 2, 3. Okay, so what's the overall charge on that nitrate ion? Negative. So how will I get a negative 1, right? So how will I get a negative 1? Okay, a single bond to an oxygen, right? What will these two be? Perfect. Okay. Wonderful. Okay. She did something that's beautiful on her part. And yeah, if you had this in your little toolkit, then you don't have to struggle, because all these years, like, I see people kind of try to struggle how to do this. But I'm thinking, if you know single bond oxygen is minus 1, and there you go, here's your minus formal charge, right? There's your minus formal charge. All right, let's make sure we have 24 valence electrons now. Okay, so count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We got it. All right, let's do our formal charge for this nitrogen. Okay, ready? 1, 2, 3, 4, 5. What is nitrogen happy at? 5. What's 5 minus 5? 0. Okay, let's do the octet rule for this nitrogen. Okay, ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's okay. That's okay. We'll call this an expanded octet. That's okay. It's an expanded octet. Nitrogen can do that. Okay. Do you want me to do the oxygen and formal charge and octet rule? Okay. We'll do it for this double bond. Okay, ready? Ready? 1, 2, 3, 4, 5, 6. What is oxygen happy at? 6. What's 6 minus 6? 0. So the formal charge on that oxygen is 0. Let's do the octet rule for this oxygen. Ready? Count everything individually. 1, 2, 3, 4, 5, 6, 7, 8. The octet rule is satisfied for that one. Okay, it's the same thing for this oxygen because it's a double bond. All right, let's do this oxygen here. Okay, ready? Formal charge. Okay, ready? Formal charge on this oxygen. 1, 2, 3, 4, 5, 6, 7. Do it again. 1, 2, 3, 4, 5, 6, 7. What is oxygen happy at? 6. What's 6 minus 7? Okay, there's that negative 1 formal charge. Which The problem tells you has a -1 charge, by the way. All right, octet rule. Okay, ready? Octet rule for this oxygen. Count with me. 1, 2, 3, 4, 5, 6, 7, and 8. 7 and 8. Okay, that has an octet rule. Satisfied. All right, so this is not the full right answer. Okay, it's one of 3 right answers. Okay, because you see, everyone, I just put that single bond here arbitrarily on the, what is that, the right-hand oxygen. Where else can that single bond go? In the middle. Okay, so this is an example of resonance. All right, so if I want it in the middle, here's what I'll do. I'll put the single bond in the middle. I'll put this pair of electrons here, and I'll kick this pair of electrons out. So now I'll have my single bond in the middle, or the down. Okay, so let's do that. And don't forget, when you do resonance, you have your bracket and this back and forth arrow. Okay, because these structures, literally, it's the same thing. I mean, all 3 structures are equally valid. So single bond at the down in the middle, right, Alex? Okay, so now this has the minus formal charge. Okay, this has the double bond. Okay, I left this one alone. Okay. All right, what's the last one? So I had a single bond down. What's the next one?
Left.
The one on the left. Okay, for the one on the left, we'll put this one here and kick this out there. The one on the left, and I think those are the 3 resonance structures. The one on the left. This is your example of resonance. Okay. I want to tell you this. Look at this minus formal charge. It's on this oxygen. On here, it's on this oxygen. And then on here, it's on that oxygen. You see the minus formal charge? It's buzzing. It's buzzing like a bee. It's delocalized. That's the word that I'm looking for. It's delocalized across these 3 oxygen atoms. That's what gives nitrate, carbonate, all these molecules with resonance. That's what gives them this tremendous stability. Okay, tremendous stability. Why is there stability? Okay, look at that minus charge. Okay, one time it's here, one time it's there, one time it's here. So literally, it's just going back and forth, back and forth. Okay, it's not like that minus charge is being built up on one oxygen atom. The minus charge is equally shared across all 3 oxygen atoms. So that gives resonance a lot of, it's very stable. Okay, it's very stable. Let's do a couple of more examples of resonance, and then we will continue for you guys on Thursday. Okay? We'll have some sort of normal class, maybe a week when we have full class. All right, so I think this is something that, put this in the back of your mind. Single bond oxygen, minus formal charge. Double bond oxygen, what's the formal charge? 0. Nitrate. All right, let's do carbonate. Okay, another example of resonance. You remember when you made flashcards of these? Okay. Hopefully we're coming full circle, maybe. Okay, carbonate. All right, so what is carbon happy at? 4. What is oxygen happy at? 6, but we've got 3 of them, so 18. And then how many electrons? -2. We've gained 2 electrons. Okay, the -2 means we've gained 2 electrons. So our goal is to get 24 valence electrons, 24 valence electrons around the carbonate ion. All right, what will be our center atom? Let's make our center atom carbon, because we really don't know which of the 3 oxygens are going to be center. So we'll make carbon our center atom. Okay, and we will do 3 oxygens. Okay, carbon loves 4 no matter what. Okay, 1, 2, 3. Okay, what can we do for carbon to get 4? Carbon loves 4, right? So we already got 3. 1, 2, 3. So what shall we do next? Yeah, a double bond. Very good. Okay, so I'll do it here, but because of resonance, we can have it down and to the right as well. Okay. Yeah. So, all right. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 9, 10, 11, 12. Okay, double bond oxygen, remember? Double bond oxygen. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Single bond oxygen. Single bond oxygen. 18. 19, 20, 21, 22, 23, 24. And this is my -2 here, right? Everyone see that? -1, -2, there's my -2. Okay, let's do octet rule and formal charge for this carbon. Okay, formal charge, 1, 2, 3, 4. Carbon happy at 4. 4 minus 4 is 0. Octet rule for this carbon, 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule for this carbon is completely satisfied. All right, this oxygen here, ready? Formal charge. 1, 2, 3, 4, 5, 6, 7. What is oxygen happy at? 6. What's 6 minus 7? -1. Okay. Same thing with this oxygen. Everyone see that? Octet rule. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. Same thing with that oxygen. All right, how about this double bonded oxygen guy? Formal charge. Okay, 1, 2, 3, 4, 5, and 6. Once again, formal charge. 1, 2, 3, 4, 5, 6. What is oxygen happy at? 6. 6 minus 6 is 0. Okay, the octet rule on this double bonded oxygen. All right, count with me. 1, 2, 3, 4, 5, 6, 7, 8. Anytime you do the octet rule, you count everything as 1. So 1, 2, 3, 4, 5, 6, 7, 8. Octet rule satisfied. All right. Resonance. Okay, we'll make the double bond. I'll have the double bond here, but I can also have it down, right? So let's do it down. So to make it go down, I'll move this one here, kick this out there. And don't forget your back and forth arrows. this double bond down, okay, we'll now have 2 lone pairs. I did nothing to this oxygen, so I'll leave it like that. So here's my -1 and -1 for -2. And then one more, I'll have the double bond this way on the, the right oxygen. So in order to do that, I'll move this pair of electrons here, kicking this out there. And this is my final resonance structure. Okay. Look at the minus charges here, okay? Look at the minus charges, how they are just sort of delocalized, okay? Delocalization. That makes the carbonate ion very, very stable. All right, let's do one more resonance, and then we will do more practice on Thursday. And then next week, we'll really wrap up the class. All right, phosphate ion is our next and last one for today's class. Okay, phosphate. Okay, phosphate is found in our bodies, okay, important molecule. Phosphate is PO4 minus 3. And this is called the phosphate ion. Okay, another example of resonance. All right, so what is phosphorus happy at? Okay, phosphorus is happy at, it's below nitrogen. So if it's below nitrogen, nitrogen is happy at 5. Phosphorus will also be happy at 5, okay, right below nitrogen in the periodic table. Oxygen is happy at 6, but we got 4 of those for 24. And then the -3 means we've gained 3 electrons. Okay, the -3 means we've gained 3 electrons, so +3. So we got to get 32 valence electrons around the PO4 minus 3 molecule. We got to get 34 of them. Okay, I'm going to choose phosphorus as my center atom because I don't know which of the oxygens will be center. Okay, so we'll choose phosphorus. All right, now think about this. PO4, right? 1, 2, 3, 4. Okay, how will I get to -3? Okay, and what about the fourth one?
It'll be a double.
Fourth one will be a double bond. Okay. Very good. I think you're getting it. So what a single bond oxygen? Okay, we'll have 3 lone pairs. Right, so let's do this. I've seen students try to figure this out. They do all this. Maybe this will help. Maybe it won't. I don't know. But okay, don't forget the minus, and minus formal charge. And then the double bond oxygen, notice there's going to be 2 lone pairs, okay? Okay, let's make sure we have 32. Okay, Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 31, 32. All right, we only have one more minute, but the resonance double bond here on the left. Let's put a double bond up top really quickly, and then all right, this has 4 resonance structures. Double bond on the left, double bond on top. Let's do double bond on the right. And finally, I'm having the double bond at the bottom. Don't forget your back and forth arrows, because the idea is that this thing, those negative charges are like bees buzzing around a beehive. Okay, they're just that's essentially what delocalization is. Okay, so that's why these resonance structures, phosphate, nitrate, carbonate, pretty stable. Because that negative charge is moving all around. It's delocalized. Those are the 4 resonance structures of phosphate. Okay? Look how the minus charges are delocalized across all 4 oxygen atoms. So I'll see you here on Thursday if you'd like to come. If not, watch the video. And if just Thursday is just more practice. Hopefully by this weekend I'll have a study guide up for our 4th exam. Okay, thank you for coming. And whatever is missing on Canvas, make sure you turn that in so that I can put some points in. I'll see you guys on Thursday, just for more practice. All right, bye, Alex.
See you later, Doctor.